All right, we're continuing on. We are on page 120, seal welds. It's kind of an odd place to put this, but according to the book, it's in the same spot. And I'm trying to, instead of bouncing around a lot, I'm trying to make sure I follow kind of like with the book and the PowerPoint as we're lecturing along, so it's less confusing as we do this, okay? Seal welds are continuous welds running the entire length of a riveted joint seal. Usually single pass welds deposited along the rim of the joint, not expected to carry a heavy load, intended primarily to provide leak tightness. So in this case, you can see there's two plates, there's a rivet here, and what happened is they sealed it up so that the amount of material and dirt cannot be forced inside of here, along with moisture, and of course, you know, depending on where you're at. If the moisture gets in there and it freezes, it'll expand, shrink back down, expand, shrink back down, putting more and more pressure upon this rivet and kind of testing its tensile strength and its ductility as well. So the seal weld helps kind of keep it in place, keep material from coming inside of it, and so forth. They're not expected to carry a heavy load. All right, moving back on to groove weld. Excuse me. Figure 4-10, page 120. It's kind of what we just talked about, but now we're going to add a couple more things into it, okay? For example, this is only a 3/4 inch piece of material. So if we were to say, what groove size is this? What weld size is it? 3/4 inch weld. 3/4 inch material, 3/4 inch groove weld. Even though we know that we have face reinforcement on the top side, this is our face reinforcement, this is our root reinforcement. We have them on both sections, doesn't matter, still 3/4 inch weld, okay? So that's our weld size. We know that the face is on the top portion of the weld, okay? So looking down upon the weld, if that were a three-dimensional weld. Fusion beyond the groove face. Usually you do not see this worded like this. This is in the code book. So one of the reasons that this matters is, according to AWS D11 code, most welds in this situation cannot exceed 1/8 of an inch past groove face, okay? So 1/8 of an inch on this side, 1/8 of an inch on this. If it gets wider than that, it's considered a rejectable weld. And I will tell you this in the shop several times. I'll say, it's too wide, you know, it went past that limit. Let's really bring it back in. Let's watch where we're going. You want to bring it right up over to it. Just watch that weld come over and melt right into that, the edge. Do not get any wider than 1/8 of an inch on each section, okay? Depth of fusion, again, is this section here, okay? As welded, this is the fusion face. Before welding, it was the groove face, okay? Now you notice that's the groove. Look what we have here. I'm going to tell you that as we get into groove plate, you'll start putting what's in the trades, the slang terminology for it's a land, okay? But the real terminology for it is, the correct terminology I should say, definition, is a root face, okay? So the root face is this big. I may tell you to put 1/8 of an inch land or a root face on this, depending, especially welding, shielded metal arc welding, open, root, flat. Now when you get into overhead, I may have you put like a 3/32 on it, so forth. And I'll show you that in the shop as we're going along. But it's all kind of starting to come together, okay? The root opening as well. What's the width of our root opening? Naturally reinforcement, this side being our root reinforcement, this side being our face reinforcement. The toes of our weld. This is the root toe, both sections here, okay? All right, I think we pretty much broke that one down. Remember, the biggest portion of this is making sure depending on which code application, you're not allowed to exceed 1/8 of an inch past groove face. So as an inspector, I may come up, as I'm giving a test or even documenting as I'm watching a weld, if I have sign off on it, I will say, take a measurement and say, groove face 3/4 of an inch wide. So now I know 1/8 inch each side. If it's wider, if the weld is wider than 1 inch wide, it's right at borderline. If it's 5 thousandths over, or typically I'm measuring with a 1/32 scale, okay? When I'm measuring those situations. But say it's 1 inch, 1 and 1/32, it can be a rejectable weld, okay? When we start getting into the undercut and so forth, we're talking 31 thousandths of an inch deep. So 1/32 deep of undercut is rejectable, and so forth. So it's important that you understand the terminology and the math, measurement and the math that is involved in the trades. Moving on. Proper reinforcement should not exceed 1/8 inch width of groove weld, should not be more than 1/4 inch greater than the width of the groove face. Right there is exactly what I was mentioning earlier, 1/8 inch each side. The width of the groove weld should not be 1/4 inch greater than the width of the groove face. Now, this is AWS's code. You go to API and it's 1/16 only on each side, so 1/8 inch total. Okay? ASME depends on the application, whether it's pressure piping or process piping. Those will change as well, along with the base metal sometimes, Inconel, Monel, and so forth, okay? So again, we're looking at 1/8 inch above. A lot of times in this situation, what I would do is I would cut from here to here, make sure that I'm not 1/8 inch, exceeding 1/8 of an inch above that. Here's what we talked about earlier. It can be 2 different size groove welds, and this does happen from time to time. They're not always equal lengths or equal width sides. All right. So now we are moving on, page 121. Excessive reinforcement above allowable limit is a waste of time and weld material, and also decreases working strength of joint because of the concentration of stresses at the toe of the weld. No undercut, no overlap with the toes. Over here, not less than flush with plate surface. Okay, you're going to get my vibration speed. Okay? Why does it matter how large the weld is and how much reinforcement? Okay? So, everything in this world has harmonics to it. Okay? And we can get into a lot crazier terminology. We're not going to do that. I'm just trying to explain something so that you understand where we're coming from. So please don't get hung up on the terminology, especially if you're an engineering student. We could go into a lot more depth. We're not going to. We're going to talk about welds, okay? So I'm going to draw a goofy weld here. All right. So this is our weld pattern. Okay. So we have a weld coming along here. And if you notice on the left-hand side, there's a nice gradual transition. On the right-hand side, it looks kind of like an ice cream cone, right? Well, there's an important factor to that. Let me try to turn this light on and see if that helps at all. Okay, it does. Okay. So we talked about harmonics and how everything has vibration. All right? So now considering this as a solid weld, now that it should be, theoretically, one big piece of metal. Especially depending on welder's skills, okay? So when I tap that, I just send a vibration through it. Even our voice is vibration through the air, okay? Even metal, as strong as it can be very porous. It has vibration, it'll send vibration and signals through that. Most of us seen that. We hit something, boom, okay? So what happens is vibration comes down through here. As long as everything's going good, and it's a nice straight piece, it should stay in somewhat of a even path flow. Okay? Now this right here is a piece of porosity, and let's say this is a piece of slag or a lac of fusion. It's kind of following the groove face like a lac of fusion, all right? So this piece is coming down, and it has to bypass this. This piece is coming down, it has to bypass this. And this one's coming down nice and even. But if you noticed, all of a sudden, this vibration path and this vibration path, because of this discontinuity, got smushed closer together. So now the intensity is right here, okay? So I want you to think of that intensity of a vibration as a fishing pole. If we take we're holding a fishing pole, and we shake just a little bit here, longer we are, the end of that fishing pole shakes a lot, moves a lot more drastic, correct? It's kind of the way vibration works, is that we condense things, sometimes we'll condense stuff to one point, and it can have a dramatic effect at the end, especially when there are interruptions as well. If you also notice that fishing poles will start out real heavy, and they condense the vibration to a fine point at the end. Okay, now fishermen, you like this with a lot of control, so forth. They build them for a lot of different things, action and so forth. Vibration, again, is still condensed. So we kind of know why discontinuities are a problem now. But what about weld reinforcement? Why does it have to stay within that 1/8 of an inch? Because they've tested and proven that if you keep it within a 1/8 of an inch, then the vibration is not dramatic. There are no major effects that are going to alter that to a point, typically, to where it's going to be a traumatic event or a failure or something like that. However, when we have a weld that is excessive, let's look at what happens here. It's going to follow along, and wow, all of a sudden it got hit here, just like water hitting on the side of a beach, okay? So we'll come back to that, and then all of a sudden more. It's all condensing right here, you see? So that's what happens, is now all that vibration is forcing here, so we see stress points that we're going to start noticing and looking for, and we're doing industrial maintenance and repair work and so forth. So right here, this is going to be one of the first places I look for a crack. When I come up to a skyscraper, a piece of equipment, a shaft, a bearing, anything, I'm going to look for stress risers, just like this. So what happened is you have risen the stress in this area, you've amplified it and pinpointed it to right there. Okay? And the rest of this, now there's gradual patterns, and I guess that one shouldn't have went through there. But say there's a couple more in here. So there again, there again, there again. Notice the patterns, kind of see how we're gradually putting stress on that, okay? So here's a really good comparison. This is one I use a lot in class. Think of the water at the ocean on a beach, okay? We're not too far away from the beach here. When I was in Wyoming, there was a lot of people who had never been to a beach, so it was more than likely everybody here has been to a beach, they're going to know what I mean. If you have a nice gradual sandy beach, when the water comes up to it, it comes up nice and even. I mean, there's some tidal waves and so forth, but again, it comes up and then it comes back down. And the majority of the sand and the dirt stay on the ground as the water just flows back out, right? A nice, easy transition in, transition back out. What happens when you have a bank there? The water slams against it, slams against it, and then it'll erode away at the material. Well, that's exactly what happens here. I know it's metal, but it's the same thing. When that wave comes in and hits this, it's eventually wearing away and eroding at this material. Now, if this was a piece of pipe and the internal structure looked like this, then we would have fluid quite literally coming in and washing that out. And it does happen, especially with stainless steel welds. It's also a reason why we got to watch our root reinforcement inside of a pipe as well, okay? So this is just a good breakdown, and we start talking about stress risers, why it's important, basic types and joints. You know, we're going to get further into this in other chapters as well. But we have to start this conversation now and get you thinking that way so you understand. All right.